Hello, everyone, and welcome back to our channel. Today, we are excited to walk you through an essential concept in automotive cybersecurity, that is layered security. You have seen us talk about secure boot, IDS, OTA updates, and more. But how do all these fit together to build a strong defense? In this session, we'll explore how these controls are structured across different layers to ensure end to end protection. With that, I'll hand it over to my colleague Dharmesh to take you through the details.
Yeah, thanks, Bhumika, for the overview. So, when we look at the automotive cybersecurity from the layer perspective, the security architecture can typically divided into four distinct layers, as illustrated on your screen. So, the innermost layer is the issue electronic control unit level, so which represents the vehicle's embedded hardware. Securing this layer involves safeguarding the physical components and ensuring that the integrity of the hardware platform remains intact. Moving onwards, the next layer is the internal communication, where various issues within the specific domain, such as powertrain, body, or ADAS, exchange the data. Protecting this layer is critical to prevent unauthorized control or data manipulation between these systems. And the third layer is the gateway, which acts as a central node connecting multiple vehicle domains. So it plays a crucial role in the enforcing communication rules, applying filtering, and managing diagnostics and update request across the domains. And finally, we have the outermost layer, which is the external communication interfaces, which typically include the infotainment system, telematic unit, and the V2X module. So this layer is most exposed to the outer world and therefore a primary target for the remote attacks. So in our past videos where we discussed about the reports from upstream, we had seen that most of the attacks, almost 90 to 95% attacks were happening through the remote. Uh, to effectively secure each of these layers, what I have discussed, the industry follows the defense in depth strategy, a multi-layered approach to mitigate threats and every level of the system. So this strategy is supported by five fundamental pillars, which are the physical security, so ensuring tamper resistant hardware through robust design, some security measures like secure boot, protection against the physical infrastructure, or a reverse engineering. The second important pillar is the network security. So implementing firewall, message filtering on the intrusion detection or prevention systems at key nodes like gateway or domain controllers will come into network security. Next is the software security, so which is enforcing the secure coding standards. For example, we have the guidelines like MISRA or SASC, performing the rigorous testing and managing the software updates securely or reduce the software vulnerabilities. Then comes the cryptography. So cryptography is strong cryptographic protocols such as the TLS or IPsec and the secure onboard communication to ensure the authenticity, confidentiality, and the integrity of the message. And the last pillar is the monitoring and the response. So continuous monitoring the system for anomalies or any kind of tracking you do to detect that there is something uh, not going as per the expected, and then you can rapidly respond the uh, whatever the threat you identified. So these are the five pillars which is used for the defense in depth mechanism, and which is used in the current industry. So in past our videos, we have discussed about the various cybersecurity controls or mechanisms, measures that can be used. And when you generally do the Tara analysis for your project, cybersecurity loan project, uh, what we are going to discuss today will come into handy when you do the residual risk analysis. So where you have to decide like which layer or which cybersecurity mitigation you will place in order to reduce the risk. So that's where whatever the discussion we have done, we are doing in this video, it is like overview of each of these cybersecurity controls or measures and where it fits in this cybersecurity architecture, layered architecture, where you can map them. So in each slide, we'll go through the overview of the each cybersecurity control. But if you want to see the detail level or you want some more details about each cybersecurity controls, then please follow our previous videos for each of the topic we already discussed. So now let's move into the
Maybe
each
there.
cybersecurity.
Okay, so Dharmesh, I
Hmm,
have a question here. So on the left side, we see different layers, be it ECU or gateway
mhm,
or external communication. And on the right side, we are seeing the defense in depth. Yeah, there are five
mhm.
of them listed. Um, whether whatever we have listed, the things on the right side, do they belong to only one of the layers in the left side, or is it generic? It can come in any
Uh,
of the layers here.
Yeah, it is generic, so it can come across all the levels, depending on the which cybersecurity mechanism we are using. So based on that, it will come. For example, when we talk about the secure coding, so secure codings comes at the issue level also, or when we have software for gateway, then also it comes under the gateway. Uh, Also the cryptography, when we talk about the cryptography, it will also come in the TLS when we are doing the external communication to other network or backend system. There also cryptography is used, and also when the issue when we are doing the protecting the data, there also cryptographic operation required. So these are generic, and it will come across the all the levels. It's depend on the which security measures we are using.
Okay.
Okay, then moving on. So let's first discuss the role of the intrusion detection systems or IDS. So in the context of automotive cybersecurity, IDS act as a surveillance mechanism with the vehicle communication infrastructure preliminary at the gateway level. Think of as a security camera system for your network, constantly monitoring that data flow and the system behavior to detect any anomalies or malicious activity in your network. So the IDS doesn't actively block the threats, but plays a crucial role in early detection and altering, helping us to respond to potentially breaches before significantly damage occur. So for a layer security perspective, IDS supports the three core cybersecurity objectives. We call also the cybersecurity properties, which is nothing but the confidentiality, integrity, and availability. So by flagging the suspicious activities, it prevents the unauthorized access to sensitive vehicle data, which is nothing but confidentiality we are protecting, identifies the data tampering, so which is nothing but the integrity, and ensures that the malicious actor do not degrade the performance or accessibility to the system, which is availability. So with this cybersecurity control measures, in implicitly you covers all the cybersecurity uh, objectives, confidentiality, integrity, and availability. Because modern vehicles are connected to external networks and house complex internal communication pathway, the gateway serves as a central point for the data flow. And deploying IDS at this level enables the comprehensive visibility on both the internal and external threats. So when integrated with broader incidents response strategy, IDS provides us the real-time insight that aid to tracking the attack vectors and preventing future exploitation. So it doesn't mean that you can deploy the IDS system only at the gateway, but as a recommended, if you have deployed the IDS system at the gateway layer, then it would be like you cover most of the uh, communication flow between the domains. So there are some IDS mechanism you required for at the domain level also. So that is also possible, but yeah, it is recommended that you can use it at the gateway layer. So in practice, IDS can be rule based or anomaly based, and we also discussed this about in detail, like which kind of IDS mechanism are there and what are the things involved. So if you go through our videos on IDS, you will come to know in detail like how IDS works and where it fits. So that was the overview about the IDS and where it fits in the layered architecture. Next relevant is the intrusion prevention system, so which is IPS. So in contrast to IDS, which detects the intrusion, and the intrusion prevention system takes a step further, actively blocking or mitigating the threat in real time. So position this also at the gateway layer is recommended, where the external and internal communication coverage are more. So IPS act as a protective firewall that doesn't just monitor but also responds to malicious activity. It's like having a security guard at the entrance, not just watching who is entering into house, but also stopping the intruders before they cause any harm. So the IPS ensures the integrity of the data by blocking by unauthorized changes, preserving the availability by preventing denial of service kind of attack, and protects the confidentiality by restricting the data leaks. So for example, if attackers tries to inject malicious CAN message into your system or flood it with the CAN packages, the IPS detects this abnormal behavior and stopped it immediately. So giving the growing reliance and the connected services like remote diagnostics or OT updates and cloud connectivity, vehicle face increasing exposure to cyber threats. So the IPS is the vital in the mitigating this risk at the earliest entry point. So that's where when you see in the project IDS and IPS both works together. So IDS also will be on place and the IPS also will be in place. So nowadays, since AI came, so there are some advanced IPS solution available which is leveraging AI. So which we also discussed in our IPS video in detail, like which kind of IPS systems we are using. There we talked about the firewalls also in detail. So you want to know about more, then yeah, please follow that video. So yeah, when we talk about which layer it fits, so it fits at the gateway layer along with the IDS. Now moving on to the next cybersecurity control, which is the secure boot. So the secure boot protects the process itself is uh, making vehicle ensuring that only the trusted and the verified software runs during the startup phase of the issue. Think of it like a digital passport control system in the airport. So before any software is allowed to enter and run, it identifies that with the cryptographic signature, against the list of approved entities. If it is matching, then only it will allow you to run. Otherwise, if the software isn't signed and authenticated, then it blocks from the execution. So this process ensures that the vehicle system start with the clean, uh, untempted code or forming the foundation for the secure operating environment. So this is very important cybersecurity controls, and this is required whenever you do, let's say, firmware over there update or secure flashing. Then the precondition would be to use this secure boot. So that is the starting point. So it is also helpful for the other security measures, which anyway we'll go to discuss bit on the further slides. So this where it operates. So this operates at the issue layer. So it protects the system integrity by verifying that the digital signature or bootloaders and firmwares are did not tampered during any kind of uh, communication. So it is also ensure the authenticity, meaning that the software truly comes from the trusted source, such as the OEM, and it doesn't come from the attacker. So this is also an important cybersecurity measures, and it comes or where can you map it? So you can map it at the issue level. So relevant topic. Next measure we will talk about our secure flash. So secure flash ensures that any software or firmware update applies to the vehicle issue are both authentic and safe. So when the manufacturer releases new software update or its patch, a feature enhancement or let's say security fix, it must securely return to the memory of the issue. So secure flash guarantees that this process is protected from tampering and unauthorized modification. So this mechanism works through cryptographic techniques. So when we see defense in depth, we use cryptographic. So there, uh, this particular security measures uses the cryptographic techniques to ensure that only the valid software is going to flash in your issue. So first, the update package is digitally signed and often encrypted. So upon reception, the issue verifies that the digital signature, confirming that the software origin uh, is authentic and ensuring is haven't modified in the transition. So that will ensure your integrity. So encryption protects the content of the data during the transmission, maintaining the confidentiality. So secure flash is essentially important in modern vehicle that are highly relies on the software, where updates can directly impact safety critical functionality such as the braking or steering or engine control. So a compromise update mechanism could allow a hacker to install the malicious code, compromises the vehicle operations. So secure flash will prevent such scenarios. So how this secure slow flash works also we have discussed in detail in one of our previous video. So with increasing the regulatory focus on cybersecurity, such as the UNSC regulation R15156 for the software update management system, secure flash is not just a best practice, but it is also compliance requirement. So we also discussed in the video we have done for the UNSC R155 and 156, where secure flows is now mandatory requirements. So it's plays the key role in upholding the security posture of the vehicle over its life cycle. And next, the relevant security measures is the over-the-air update. So over the app or over the air update allows the manufacturer to remotely deploy the software update, fixes, and the new features to vehicle without need for going to the workshop visit. So while this improves the convenience and customer experience, it also introduced new security risk. Hence, the need for a robust protection mechanism is needed. So OTA operates across the multiple layer in the architecture. So it doesn't, whichever the cybersecurity measures we discussed previously, those were mapped to particular layer. But OTA is the one which is involving all the layers, starting from the cloud, so which is the external communication, to the gateway, and the finally at the individual issue level. So throughout this journey, the update package must be protected using the cryptographic technique to ensure its confidentiality, integrity, and authenticity. So cryptographic signing of the update files ensures the authenticity, confirming that the update origin is trusted and coming from the trusted source. Integrity ensures that the file hasn't altered, and the encryption protects the update from reverse engineering during the transmission. So a secure OTA infrastructure required coordination between these multiple systems, backend system, telematic unit, gateway, and issue. So each component must participate in the secure authentication, validation, and logging mechanism to track updates and enable rollback in case of failure. So how does this work and how PKI is involved? All these things we have discussed in our OTA in detail, how OTA mechanism works. But when we want to map the layered wise where it fits, so it will come into each layer. So because it involves the multiple systems and multiple layers, so that's where it you can map it to all the four layers. And next we have TLS, which is the transport layer security. So the transport layer security is a backbone protocol for secure communication over the external networks. So in automotive environment, TLS is the most relevant in the telematic and the infotainment domain, where vehicle is connected to cloud, smartphone, or any third party services. So TLS ensures that the data exchange between a vehicle and the external server remains the protected and tamper free. So TLS uses the encryption to maintain the confidentiality, meaning that no third party can view the content of the data being transmitted. This is crucial when sending sensitive data such as location or diagnostic user credentials or even over the air update packages, etc. So additionally, TLS provides the integrity by using the cryptographic hashing to detect whether the data has been altered in the transmit, and authentication to verify that the identity of the connected servers is authentic. So in practical terms, when vehicle connected to backend cloud servers to download a software update, uh, it will check the remote command or synchronize the telemetry data. So TLS ensures that the session is secured before you establish any kind of communication with the backend server. This protocol will ensure you have secure channel, and via this channel then you can do whatever operation you want to do. So in case of if man in the middle attacks will happen, then also it is protected. So your data is protected and it is in the secure channel. And this mostly relies on the certificate authorities. So how does this works, and how TLS handshakes will happen, which we already discussed in our previous videos. So whenever in the embedding, it's virtually every secure communication stack and aligns with the industry best practices as well as the security standard like ISO SA 21434 have recommended that you can use TLS for the secure communication to external world. So moving on, next cybersecurity measure would be secure storage. So secure storage is all about protecting sensitive data at the rest within the vehicle's system, especially in the issue and the gateway, because that's where there will be a chance when it's switch off during that time somebody can get hold of the data if they have the physical access to particular device. So to protect that, it is recommended that you can implement secure storage cybersecurity measure. The confidentiality aspect of secure storage means that data stored in the memory, for example, flash or EEPROM, is encrypted so that the even attacker gains the physical access to the hardware and get hold of your data. They cannot able to decrypt it. So it should be confidential. So that's why encryption is required on your data. And when we talk about where it can be mapped, so it can be mapped two layers, issue layer and gateway. Uh, Automotive security storage often leverages features like hardware-based security module like HSM. So we also discussed the HSM TPMs, trusted platform modules, during the secure storage measure video. So this is also critical cybersecurity control. Then moving to the next cybersecurity control, which is nothing but our secure diagnostics. So secure diagnostic introduces access control and security checks into the diagnostic processes, ensuring that only the authorized entity like OEM tools or certified garages can access or alter the diagnostic information within the issue. So without this layer, attacker could inject the malicious diagnostic services to extract the sensitive data, disable particular component, or rewire the memory. So traditionally, UDS Unified Diagnostic Services Protocol exposes a wide range of functions, starting from the reading of the memory, initializing the software updates, uh, actuator tests, etc. So while useful for legitimate services, uh, they present a serious attack surface if let's it left to unsecured. So that's why it is very important that a diagnostic also should be secured. So before uh, there were no possibility for attackers, or there was not at all cybersecurity concept was there. The UDS or OBD connectors was outside of the car, then it moves to the inside of the car, but still it is not secure. So that's where we talked about in one of the video about the different scenarios, how attacker can exploit this so, diagnostics services, and that's where security services like 0x27 and 0x29 was come into picture. So 0x27 was already there, but it has some of the loopholes, or some more protection was given. So that's why the new service in the year 2020, UDS have introduced the 0x29. So on detail on both these services, we have discussed in the secure diagnostic cybersecurity measure, what we discussed in our earlier video. So if you really interested how this services works, you can please go through our video on secure diagnostics. And coming to where this can be fit into this layered architecture, so it comes under the issue because the diagnostic communication happens to the issue, and that's where the security measures will be in place. So next measure we will talk about is the SECOC, secure onboard communication. So SECOC is a critical control designed to protect the communication between the issue and inside the vehicle with the different issues. So when they communicate, so how this communication would be protected. So that is done via the SECOC. And as the modern vehicle adopt the service oriented architecture or zonal designs, the internal communication becomes richer, faster, and more vulnerable. So SECOC ensure that this communication is authenticated, tamper proofed, and confidential, therefore by preserving the system trust model. So at this core of the SECOC is the message authentication code, which is MAC, and into the communication protocols like some IP or CAN-FD or Ethernet. So we can protect the communication for these of the protocols over the SECOC, where while sending, you will have the message authentication code, which is attached to your data, and at the receiving end you will have the mechanism to verify this message authentication code, which will ensure that the communication happens between two issues are not altered. Also this will be like there will be a freshness value manager, so which will ensure that if the same packages are flooded, then it will reject the other packages. So denial of service attack also can be prevented using the SECOC. So SECOC also very important cybersecurity measures, and this when we map to the layers, it will be mapped to the internal communication because this is applicable only within the vehicle issue communications. Yeah, then moving on to the next cybersecurity measure, which is nothing but secure coding. So this also, like OTA, it is applicable to all the layers because this isn't like only relevant to one particular layer. As I mentioned earlier, so nowadays software part is more into the vehicle, so that's where secure coding comes into picture, and there are some standards available like Misra or Search, uh, so which will give you if your code have any vulnerabilities, you have to adhere those rules in order to securely write your software. So secure coding refers to the disciplined development practices that aim to minimize the software vulnerability and reduces the attack surface at the secure or source code level. So one very good example of the secure code is we can say that one of the bug generally we see is uh, underflow or overflow. So when the coding is not properly written, and when attacker will try to find this kind of vulnerability, whether your code has any overflow condition or underflow condition, and they will try to exploit this so that they can uh, disable the functionality of your system. So that's why the secure coding is very important. So it's spun into the all the layers. So it's use internal and external communication interfaces and gateway system. So whether it is input validation on the diagnostic request, memory safety in the CAN driver, or encryption logic in the OTA components, like secure coding ensures that each piece of the software resist the exploitation. The goal is to prevent the common vulnerabilities like buffer overflows, command injection, use after free errors. So these kind of things you have to protect while you are writing the code. And as I mentioned, there are industry standards often have to other Mishra C, C++, and safety and search C, C++. So these are the security, some of the standards which you have to other when you write the s- or when you implement the software. There are some tools already available in the industry, so you can use these tools and identify whether your software have any rule violation, and you can fix this. Okay, then moving on to the last slide. So these are the cybersecurity measures. We already have discussed every measures individually in detail level. So you can please go through if you have interest to understand any of the security measures. And on the key takeaway, so we'll just map here like its cybersecurity measures, where it fits under the which cybersecurity layer or architecture wise where it fits. So OTA, as we see here, it covers or it should be mapped to all the four layers. Secure boot would be mapped to the issue. Secure flash and secure diagnostic also goes to the issue. Secure storage is basically you require at the issue and the gateway layer. The SECOC is comes under the internal communication. Intrusion prevention and intrusion detection system both comes at the gateway layer, and TLS transport layer security would come at the external communication layer. So these are the way you can map each cybersecurity controls to respective layers. So yeah, I think we are done for this topic. Then if you have any questions, then yeah.
Yeah, so I have a doubt regarding what do you mean by residual risk?
Hmm. Yeah, that's
All right.
the good question. Yeah, so initial discussion I have mentioned regarding the residual risk. So if you would have worked on the project for threat analysis and risk assessment, so in any cybersecurity relevant project, the first thing would be when you define the or do the analysis for your system or at the vehicle level, you first come up with the cybersecurity risk. So is there a risk in particular component or in which level? And based on that, you will derive the particular risk value. And it doesn't necessary that every component or every analysis you have done have the higher risk. So risk will be from the lower, medium to the high. And if the risk is high, in that case you have to reduce that risk. So there are three options: either you can transfer the risk, or reduce the risk, or ignore the risk, or you can share the risk. So if you can agree with the stakeholders and decide like what is the criteria for which risk value is acceptable or not acceptable, which one we want to reduce. So when you want to reduce the risk, you have to apply some kind of cybersecurity measures. So once you apply the cybersecurity measures, you again analyze everything and then come up with again how much percentage of the risk is reduced. If it is below your expected risk value, or again you have to apply some more cybersecurity measures and do the analysis again. So this again and again doing the threat analysis and risk assessment is nothing but your residual risk. So when you calculate the risk first time, it is cybersecurity risk, but second time again you after applying the mitigation, you again perform the uh, analysis, and then come up with the new risk. So this is what the process called the residual risk.
Maybe
All
to
right.
add on to that, what Dharmesh said, I don't know, Dharmesh, if it is similar to how it is done in functional safety,
Mhm.
because of course, when you identify any risk, you identify a control mechanism in order to reduce the risk, right? But at the end, after you do a number of steps, because you told about an iterative process, you go through the cycle again. Even after that, some kind of a risk remains, which is of very low impact, right?
Mhm.
Isn't it? This is something called as a residual risk, which means there is still some risk,
Yes.
but we decide to live with it because it's not really causing such a big, you know, issue or something like
Yes.
this.
Yeah, exactly. Yeah, it's pretty similar to that. Yes.
Okay.
All right, I got it. I have another question. Like, is it necessary to implement all cybersecurity measures to be for a project to be considered cybersecurity compliant?
Yeah, that's interesting question. So if I answer, then the straight answer is no. It's purely depend like what kind of cybersecurity measures you will use based on the your analysis. So each measure is actually preventing or placed at the particular level. And if your system doesn't have that particular functionality, then you really don't require any cybersecurity measure for that. So if let's say also it's also depend on the how your project how much you want to uh, overall cost wise you can monitor uh, if the functionality offers two or three let's say cybersecurity measures which prevents for example confidentiality, and confidentiality will be prevented using various cybersecurity measures. But in that also you will decide like how much my budget or how much time it will take to implement particular cybersecurity control or measure. Based on that you will pick the best suitable one cybersecurity control and you will implement. So it doesn't necessary that every cybersecurity measures you have to implement in order to comply with cybersecurity uh, relevant project. And one more thing is we talked about layer wise defense. It is important because let's say if new vulnerability comes up and you have implemented one cybersecurity measure at one layer, if it is getting breached, then you again don't have anything to protect. So that's where you implement this different cybersecurity measures at different layer. So even though if one of the layer is get compromised, still you have some protection to avoid any kind of risk or uh, attacker can harm the system not that much. So that's where I would say the cybersecurity measures you select and implement.
Uh, all right, thank you.
So I have a question, Dharmesh.
Hmm.
Do existing cybersecurity standards explicitly refer to or mandate the implementation of these specific cybersecurity controls?
Yeah, that's also an interesting question. So to talk about the standards, basically standards will give you the overview like what you have to do or follow, but it doesn't directly state that how it should be done. So the how part is the will be figured out by project and organization, like how this particular feature would be implemented and what cybersecurity controls will be in place. So the standards will just state that okay, I need to have uh, let's say when we talk about ISO 2144, they state that uh, your system should be protected whenever backend communication is happening. Now, with securing this communication to the backend server, which cybersecurity controls you will place, that is up to you. You use TLS protocol or simply the encryption way over secure channel. So that is up to the organization how they will implement, but standard will state like what you have to do. So in general, yeah, that is the thing. In some of the regulations, it is mandatory. Like for example, when we see the UNSC R155, R156 for software update process, there they have mandated that the OTAs should be in place for the issue. So if it is infotainment issue, yeah, OTA update will be there, and there it is mandated, but it is not necessary that all standard will mention that you have to implement all of these security measures.
Thank you for staying with us through today's session on layered cybersecurity. We hope this gave you a clear understanding of how multiple security measures work together to protect modern vehicles from evolving cyber threats. If you found this video helpful, don't forget to like and share. Follow us for more such insights every week. Until next time, stay curious and we'll see you in the next video.